calculate the voltage drop, use the formula voltage drop equals 2 times line length times load current times conductor resistance divided by conductor area. In this scenario, the line length is 230 feet, the load current is 30 amps, and the conductor resistance for number 3 copper conductor is 0.197 ohms per 1000 feet. Plugging in these values, voltage drop equals 2 times 230 times 30 times 0.197 divided by 1000, which equals 2.71 volts. Next, the voltage drop percentage is calculated as voltage drop percentage equals voltage drop divided by circuit voltage times 100. The circuit voltage is 240 volts. Plugging in the values, voltage drop percentage equals 2.71 divided by 240 times 100, which equals 1.13%. The voltage drop percentage is less than 3%, which is acceptable for most applications. Based on the voltage drop calculation, a number 3 copper conductor is a suitable choice for feeding the 30 amp subpanel. This wire size will provide a voltage drop within acceptable limits and ensure the subpanel receives sufficient power. In addition to the voltage drop, consider other factors when selecting the wire size. Firstly, ampacity. The wire must have an ampacity rating greater than or equal to the load current. Secondly, conduit fill. Ensure that the wire size does not exceed the maximum allowable fill percentage for the conduit being used. Thirdly, local building codes. Adhere to local building codes and regulations for electrical wiring. Alternative options. If the voltage drop is unacceptable, you can consider the following options. Firstly, use a larger wire size such as the number 2 copper. Secondly, reduce the distance between the main panel and the subpanel. Thirdly, install a voltage regulator at the subpanel to compensate for voltage drops. Let's delve deeper into each aspect to provide a comprehensive understanding. Firstly, let's dissect the voltage drop calculation. The formula, voltage drop equals 2 times line length times load current times conductor resistance divided by conductor area, is a fundamental tool. The factor of 2 accounts for the round trip of the current, traveling from the source to the load and back. Line length, measured in feet, represents the one-way distance from the power source to the subpanel. Load current, specified in amps, signifies the amount of current the subpanel is expected to draw. Conductor resistance, expressed in ohms per 1000 feet, indicates the opposition to current flow offered by the conductor material. The conductor area is represented in circular mils and is derived from standard wire tables. In this instance, a number 3 copper conductor has a resistance of 0.197 ohms per 1000 feet. However, it is important to consult the latest version of the National Electrical Code, known as the NEC or equivalent local codes, to obtain the most accurate and up-to-date resistance values for various conductor sizes and materials. Using the provided values, voltage drop equals 2 times 230 times 30 times 0.197 divided by 1000, which results in 2.71 volts. This indicates that the voltage at the subpanel will be 2.71 volts lower than the source voltage due to the conductor's resistance. Secondly, let us explore the voltage drop percentage calculation. The formula, voltage drop percentage equals voltage drop divided by circuit voltage times 100, provides a relative measure of the voltage drop. The circuit voltage, in this case, is 240 volts, representing the voltage supplied by the main panel. Plugging in the calculated voltage drop of 2.71 volts, voltage drop percentage equals 2.71 divided by 240 times 100, equaling 1.13%. The NEC recommends a maximum voltage drop of 3% for branch circuits and 5% for feeders. In this scenario, the calculated voltage drop percentage of 1.13% falls well within the acceptable limit, indicating that the voltage drop is not excessive. Thirdly, concerning wire size selection, a number 3 copper conductor appears suitable based on the voltage drop calculation. However, it is crucial to verify that the ampacity of the conductor is sufficient to handle the load current. Ampacity refers to the maximum current a conductor can safely carry without overheating. According to NEC Table 310.15b16, a number 3 copper conductor with THHN insulation has an ampacity of 75 amps when installed in conduit at an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. Since the load current is 30 amps, the number 3 copper conductor provides adequate ampacity. Fourthly, delving into additional considerations. Firstly, ampacity. The selected wire must possess an ampacity rating equal to or greater than the anticipated load current. This ensures that the conductor can safely carry the current without exceeding its temperature rating, preventing insulation damage and potential fire hazards. The NEC provides tables, such as Table 310.15b16, that list the ampacities of various conductors based on their size, insulation type, and installation conditions. Secondly, conduit fill. The wire size should not exceed the maximum allowable fill percentage for the conduit being used. Conduit fill refers to the percentage of the conduit's cross-sectional area occupied by conductors. Exceeding the maximum fill percentage can make it difficult to pull wires, damage the insulation, and reduce the conduit's ability to dissipate heat. NEC Chapter 9 provides tables that specify the maximum number of conductors of a given size that can be installed in different types of conduit. Thirdly, local building codes. It is imperative to adhere to all applicable local building codes and regulations for electrical wiring. Local codes may have specific requirements that differ from the NEC, such as requiring a larger wire size for certain applications or specifying the type of conduit that must be used. It is essential to consult with the local electrical inspector to ensure compliance with all applicable codes. Fifthly, exploring alternative options. If the calculated voltage drop is deemed unacceptable, several alternatives can be explored. Firstly, using a larger wire size will reduce the conductor's resistance, thereby decreasing the voltage drop. For instance, upgrading from a number 3 copper conductor to a number 2 copper conductor will lower the resistance and reduce the voltage drop. Secondly, reducing the distance between the main panel and the subpanel will directly decrease the voltage drop. Voltage drop is proportional to the length of the conductor, so shortening the distance will have a significant impact. This may involve relocating the subpanel closer to the main panel, if feasible. Thirdly, installing a voltage regulator at the subpanel can compensate for voltage drops. A voltage regulator is an electronic device that maintains a constant output voltage despite variations in the input voltage. By installing a voltage regulator at the subpanel, the voltage can be stabilized, ensuring that the subpanel receives the correct voltage even if there is a voltage drop in the feeder conductors. Therefore, in summary, determining the appropriate wire size for a subpanel feeder involves calculating the voltage drop, ensuring adequate ampacity considering conduit fill, adhering to local building codes, and exploring alternative options if necessary. In this specific scenario, a number 3 copper conductor appears to be a suitable choice based on the voltage drop calculation and ampacity requirements. However, it is essential to verify compliance with all applicable codes and regulations before making a final decision. Additionally, consider future load growth when selecting the wire size to avoid the need for future upgrades. A qualified electrician should be consulted to perform the calculations, verify code compliance, and ensure the safe and reliable operation of the electrical system. Remember, safety is paramount when working with electricity. Always de-energize circuits before working on them and use appropriate personal protective equipment. If you are not comfortable working with electricity, hire a qualified electrician to perform the work. Electrical work can be dangerous, and it is essential to take all necessary precautions to protect yourself and others. Furthermore, let's look into practical considerations during installation. Firstly, proper termination techniques are crucial. Ensure that all wire connections are made correctly and securely using appropriate connectors and tools. Loose or improper connections can cause arcing, overheating, and potential fire hazards. Secondly, wire pulling lubricants can reduce friction and make it easier to pull wires through conduit, especially when dealing with long runs or multiple bends. Use a lubricant that is compatible with the wire insulation and conduit material. Thirdly, support the conduit properly using appropriate hangers and supports. The NEC specifies the maximum spacing between conduit supports based on the size and type of conduit. Proper support prevents sagging, which can damage the conduit and conductors. Fourthly, label all circuits clearly and accurately. This makes it easier to identify and troubleshoot circuits in the future. Use a permanent marker or labeling machine to create clear and legible labels. Fifthly, ground the subpanel properly. Grounding provides a path for fault current to flow back to the source, tripping the circuit breaker and preventing electrical shock. Follow the NEC requirements for grounding electrode systems and bonding. Sixthly, inspect the installation thoroughly after completion. Check all connections, supports, and labels to ensure that everything is installed correctly and safely. Use a multimeter to verify that the voltage and current are within acceptable limits. Finally, let's also briefly address some advanced considerations that may be relevant in specific scenarios. Firstly, harmonic currents are non-sinusoidal currents that can be generated by electronic devices such as computers, LED lighting, and variable frequency drives. Harmonic currents can increase the current flowing in the neutral conductor, leading to overheating and voltage distortion. If harmonic currents are present, it may be necessary to increase the size of the neutral conductor or install a harmonic filter. Secondly, damping factors may need to be applied to the ampacity of conductors if they are installed in close proximity to each other or in high-temperature environments. The NEC provides damping factors that must be applied in these situations. Thirdly, surge protection devices, or SPDs, can protect sensitive electronic equipment from voltage surges caused by lightning strikes or power grid disturbances. SPD should be installed at the main panel and at the subpanel to provide comprehensive surge protection. Fourthly, power quality monitoring can be used to identify and diagnose power quality problems such as voltage sags, swells, and harmonics. Power quality monitoring equipment can be installed at the main panel and at the subpanel to monitor the voltage, current, and frequency of the electrical system. Fifthly, energy efficiency is an important consideration in modern electrical system design. Use energy-efficient lighting, appliances, and equipment to reduce energy consumption and lower utility bills. Consider installing a smart meter to track energy usage and identify areas where energy can be saved. By carefully considering all of these factors, you can ensure that your subpanel feeder is properly sized, installed, and maintained, providing safe and reliable power for your electrical needs. Remember to consult with a qualified electrician if you have any questions or concerns about electrical work.